All right, so we got a couple problems here working with finding different roots of complex numbers. And the thing to keep in mind when you're doing these is that whatever root you are asked to find is the number of solutions that you're going to find. And so keep that in mind. And the other thing to keep in mind is that your solutions are all going to be equidistant around the circle. And so just check like your angles and make sure that you are spaced evenly around the circle. So just a couple examples. We have the fourth roots of negative 625. So basically, I'm trying to find a complex number that's equal to that value. And I can rewrite that like this. Z to the fourth is negative 625. And I can rewrite the number z as r e to the I theta, because every complex number can be written as r e to the I theta. I can rewrite the number negative 625 like this. Negative 625 e to the I times negative pi, or regular pi. It's the same. It doesn't matter. It's a half circle. I don't know why I said negative pi. It doesn't matter. It's on the west side of the circle. So then what that means is I've got two things. Oh, I'm sorry. That was what I was thinking, is the negative value right there gets erased because this pi right here, if you think about going pi radians over, that's how I get the negative part of it. So 625 should be a positive number because that's the distance from 0. The pi part takes care of the fact that it's on the negative half of the number line. So what I can say then is I know that I need r to the fourth to be 625. Those are just positive real numbers. And I know that I need 4 theta to equal pi. However, I told you at the beginning of this video you need 4 different solutions. So I want you to think of, how can I get the same answer as pi? Well, I can say, I'm going to do a comma. I can get the same answer if I just land at the same angle. So 4 theta could also equal 3 pi. 4 theta could also equal 5 pi. 4 theta could also equal 7 pi. I'm going to stop there because I only need 4 answers. This value comes out to be 5, right? Yeah. And then the theta values you get just by dividing by 4. So these are my 4 different angles. And I don't need to do a fifth angle because if I added another 2 pi to get, say, 9 pi over 4, that's equivalent to the first angle I found of pi over 4. So my 4 answers then are, it asks me to find them in Euler's form, but I mean, you can find them in Cartesian form just by pressing sine and cosine. So that's the first answer, meaning sine of pi over 4, cosine of pi over 4. You'll notice that these are all evenly spaced around the unit circle, and they are all 5 steps from the origin, and that's how you do that one. Okay, the process is always the same. Sometimes people try to shortcut it and they just say, okay, the r value is the nth root of the number, and the theta values you can get by iterating this 2 pi k, where you're just adding integer multiples of 2 pi. If you want to shortcut it, you can. It's not that much longer to just build it up from the beginning every time. If you want to be fancy, you can call it de Moivre's theorem. But really, it's just sort of logical. You just want to make the r values match up, you make the theta values match up, and you need to remember that there is, for nth root, n evenly spaced values. I'll just do one more. Let's look at the sixth root of negative 1/2 plus root 3 over 2i. Okay, so that means that z to the sixth equals this wonderful thing right here. When I look at that, I know that r to the sixth e to the I 6 theta. Well, what's this r here? If I do negative 1/2 squared plus root 3 over 2 squared. Take the square root of it. I'm going to get a quarter plus 3/4, which is 1. That's the r value. So I've got 1. Now if I just sort of blindly do the arctangent, because that's usually how we find an angle for a complex number, if I just sort of do the arctangent of the y value divided by the x value, in other words, of the imaginary part divided by the real part, arctangent's going to lie to me. And the reason is because it thinks always only on the right-hand side of the unit plane in quadrants 1 and 4. So your calculator's going to think you're sitting in quadrant 4 because that gives it a negative value. It's going to think that you want as an answer negative pi over 3. But the actual answer you want is in quadrant 2. So you add pi to that and you get the real theta we care about is 2 pi over 3. I just added 3 pi over 3 to the thing. So now I have 1 e to the 2 pi over 3 times I. So I know that for my answer, my r is going to equal 1, and my 6 theta is going to equal 2 pi over 3, or if I add 2 pi more to that, so adding 2 pi is adding 6/3 pi. So it could equal 8 pi over 3. It could equal another 6 would make 14 pi over 3. How many do I need to get? I need to get 6 of them. So it could be 20 pi over 3, 26 pi over 3, or 32 pi over 3. And each of those are going to get divided by 6 to give me my 6 different answers. So the first one is going to be e to the 2 pi over 18. You can, of course, reduce that, pi over 9. Stick an I on the end. I might forget to write I on at least one of these. The next one I'm dividing by 6 again, so I just get 8 pi over 18. I guess all of these can be reduced by a factor of 2, but so if you reduce this next one, you could say it's 7 pi over 9, but you could also say 14 pi over 18. No one's really going to get mad at you. Well, I suppose somebody might get mad at you. So there's Z4, there's Z5, 13 pi over 9, just to show you can reduce it. And Z6 is 32 pi over 18i. If you added one more and got 38 pi, that'd be 2 pi more, 2/18 pi more than Z1. So you're just recirculating through what you've done before. So that's how you find n roots of any complex number. You can do it anytime. Let me know if you need any help, and I'm happy to explain.